Okay, so let's really dive into this. We're tackling one of the biggest questions there is, really. How do we think?
Right.
And for a long, long time, the answers seemed to be all about computation. The idea that the mind was just pure software,
Yeah.
that intelligence was abstract.
Symbol manipulation happening entirely inside your skull, completely separate from whether you had hands or feet or could even move. That was the dominant model for decades. But the sources we're digging into today, they show us that this framework just, well, it hit a wall.
A huge physical wall.
A huge one, yeah.
Yeah.
And the main premise, the thing that drove this whole revolution in cognitive science, that intelligence isn't some clean process happening inside us.
Right.
It fundamentally emerges.
It comes from our interaction with the world.
Through that dynamic, continuous interaction, the body, it turns out, isn't just a container for the brain.
No, it's the key. It's the hardware that actually makes cognition possible. So this deep dive is all about that massive shift in thinking.
We're basically tracking the story of how AI, well, how it failed, and how that failure completely changed how we understand our own minds. And we've got 3 big ideas to really nail down today.
Right. A shortcut to understanding the whole thing.
First up, we'll define the critical failure point of what's called classical AI and this really mind-bending problem called Moravec's paradox.
Okay.
Then we'll get into the behavior-based revolution, which amazingly proved you could build complex intelligence without an internal map of the world at all.
And finally, the big one, embodied cognition. This is the idea that even our most abstract thoughts, things like math or language, are grounded in physical experience.
Exactly. So if you want to get why modern robots need bodies and why your brain isn't the whole story, this is where you need to be.
So let's go back. I mean, where did this whole mind as a computer idea even come from? This Joe FAI thing.
Right. Good old-fashioned AI. This was the dream in the 50s and 60s. You had pioneers like Herbert Simon, Alan Newell, John McCarthy. And their goal was, well, it was ambitious, but seemed simple. Model human thinking using logic.
So thinking was just a program.
It was purely computation. You're just manipulating abstract symbols, mental representations, according to these very strict logical rules. The messy stuff, biology, gravity, the body itself, all of that was considered, irrelevant.
Just an implementation detail.
Exactly. If you could write the mind's program, you could run it on any machine. And to be fair, they had these incredible early successes.
Right, they were proving math theorems.
Complex ones. And building systems that could play chess at a really high level. And these are things that feel super intellectual, very abstract. So the promise of this pure disembodied intelligence, it seemed totally real.
So what went wrong?
Well, what's fascinating is that the problems they couldn't solve weren't the hard ones. They were the easy, everyday challenges of just being in the world. By the 70s and 80s, these programs that were geniuses at logic, they couldn't handle reality. Because the real world it's fuzzy, it's noisy.
It's not a clean chessboard. If you want a Joe FAI robot to just walk down a hallway, you have to program rules for every single possibility, every shadow, every little crack in the floor.
The complexity just explodes. It's impossible.
Right.
And this revealed the critical flaw, the problem of common sense. And this huge gap led to what we now call Moravec's paradox.
Named after Hans Moravec.
The roboticist, yeah. And the paradox is basically this. What's easy for us humans, like recognizing a friend's face or catching a ball or just walking up some stairs, is incredibly hard for machines. And the reverse is also true.
What's hard for us, like complex calculus,
is often trivial for a machine.
That is the ultimate head-scratcher. I mean, why is that? If intelligence is just symbols, why can't we just program the rules for catching a ball?
Because it's not about rules. The act of catching a ball, that's not some abstract calculation. It's based on millions of years of evolution and immediate constant feedback between your eyes, your hands, your body.
The sensor-motor loop.
Exactly. The Joe FAI approach demanded the robot build a perfect internal model of reality, calculate every possibility, then act. But that's just too slow. It's too fragile for the real world.
So the body wasn't just carrying the brain around.
It was actively doing the cognition. That was the big realization.
Okay, so that realization that the body is essential, that must have kicked off a huge change.
A complete revolution. And it was really driven by Rodney Brooks at MIT in the 1980s. He just explicitly rejected the whole idea of internal representation.
So this is what you call the behavior-based revolution.
Yep. And Brooks basically said, look, if symbol manipulation and building these detailed internal models are the problem, let's just get rid of them.
Just throw them out.
Throw them out. The shift was from seeing the robot as this disembodied logician to seeing it as a kind of very efficient insect-like reactor.
Reacting to the world instead of thinking about it.
Brooks's core idea was radical. He said that sophisticated intelligence doesn't need these elaborate, centralized world models. He argued the complexity of the behavior we see. It doesn't come from a complex internal program. It comes from the complex dynamic interaction with the environment itself.
But wait, if they weren't building any internal maps, how did they do anything intelligent? Would they just, I don't know, bounce off walls all day?
That's the genius of his method. He called it subsumption architecture.
Okay.
So instead of one giant fragile master program trying to control everything, he just layered simple, specific behaviors. They all work in parallel, and this is the crucial part. The lower, more basic layers can subsume or override the commands of the higher ones.
So we need an example here. How does that overriding make the system work?
Okay, let's take his famous robot, Herbert, the one that collected soda cans. Herbert had these simple layers. The absolute lowest layer was just avoid obstacles.
Okay, basic survival.
Basic survival. It's connected directly from the proximity sensors to the motors. The next layer up might be wander randomly. And then a higher layer was search for small metal objects.
Right.
So if the search layer tells Herbert to drive straight ahead toward a can, but the low-level avoid obstacles layer detects a table leg right in front of it.
The avoid layer just takes over.
It takes immediate precedence, overrides the driving command, and Herbert swerves. The system is always prioritizing, not crashing over its higher-level goals.
So it's always focused on the immediate present, the here and now.
Precisely.
Yeah.
And that simplicity is what let Brooks's robots, like Herbert and the six-legged one, Genghis, do things that had been impossible for those huge classical AI systems. They navigated cluttered, messy rooms.
Real-world tasks.
Real-world tasks. They didn't calculate a perfect path. They just continuously adapted.
And this whole philosophy is captured in that really provocative quote from Brooks, isn't it? The world is its own best model.
That's the one. Why waste all that time and energy building an imperfect, out-of-date copy of the world inside the robot's head when the real thing is right there, available to be sensed at any moment?
It's just a huge turning point. It shows that intelligence arises from that constant back and forth.
Yeah.
The body and the environment they're collaborators in cognition.
Right. So the behavior-based revolution showed us you can get intelligence without complex internal models for action. But our third big idea, embodied cognition, it takes this a huge step further.
It argues that the body is essential, even for the really abstract stuff.
Exactly. This is where we shift from just moving through the world to actually thinking about the world. And the core concept here is that our cognitive processes are fundamentally shaped by the specific kind of body we have.
Our sensory systems, the way we can move, all of it.
All of it. And this just blows up that old mind-body dualism that Joe Coffey I was built on. Theorists like Lawrence Barsalou, they argue for what they call perceptual symbol systems.
Okay, what does that mean?
It means that when we think, even about abstract things, our brains aren't using these arbitrary, computer-like symbols. They're actually recycling and simulating the neural patterns that we use for actual perception and action.
Whoa, okay, let's pause there. That changes everything. So if you're saying that when I think about a chair, I'm not accessing some abstract chair file in my brain.
No, you are, in a way, reliving it. You're simulating the sensory experience of seeing a chair, of sitting on one, of touching one.
And this shows up really clearly in language.
It's crystal clear in language. I mean, think about a metaphor like, she finally grasped the complex idea. The source material we looked at points to studies showing that when we hear a phrase like that linked to an action,
let me guess, the motor part of the brain lights up.
the neural regions associated with physical grasping actually activate. It's incredible.
So my brain is running a super fast simulation of grabbing something, just to understand the concept of understanding. It's grounding the abstract idea in a physical experience.
That's exactly it. Comprehension is a form of simulated action, and it goes way beyond language. Think about numbers. Our whole understanding of math is built on embodied experiences.
We counted on our fingers.
We literally learned on our fingers. We talk about numbers being higher or lower. We organize quantities in space. These aren't just convenient metaphors. They're reflections of how our physical experience provides the foundation for abstract thought.
And this has huge implications for how we learn. For development.
Huge. I mean, the work of someone like Esther Thalin showed that for babies, cognitive development, like understanding that an object still exists when you hide it, is completely tangled up with motor development, learning to reach, learning to grasp,
You can't separate them.
They're inseparable, and that's exactly why modern robots that are designed to learn, like the iCup robot, are built this way. They aren't preloaded with a database of facts. They learn about the world, how to grab something, what's heavy, what's light, by physically messing with it.
Just like a child does.
Just like a child. It confirms why JucoFAI failed. You need the body to physically ground the meaning of everything.
So if we pull all three of these ideas together, the failure of that disembodied logic, the power of just reacting to the world, and then grounding all our abstract thought in the physical body, it's not just a new theory of AI. It's a whole new theory of the mind.
It is a massive reconceptualization, and it leads you directly to this idea of the extended mind, which was proposed by the philosopher Andy Clark.
The idea that cognition isn't just locked up inside the skull.
Not at all. If it's shaped by the body and our interactions, then cognition is distributed. It's spread across the brain, the body, and even the tools in the external world we use.
And for building robots, that changes the whole design philosophy.
Completely. You stop thinking it's all about writing better software, and you start thinking about building smarter bodies. The roboticist Rolf Pfeiffer calls this morphological computation.
Which you mean?
It means offloading the computational work onto the body itself. So if a robot's legs are built with springs in them, they naturally handle a lot of the complex physics of balance. The CPU doesn't have to calculate every single variable. The body does the work.
It's the ultimate realization. The mind is of the body, not just in it.
That's the core takeaway.
Okay, let's nail this down with our study review. If you've stuck with us, you've just navigated one of the biggest philosophical shifts in the history of AI. So here are the 4 key points you need for a quick recall.
First, remember the classical AI limitation. The failure of JucoFAI was highlighted by Moravec's paradox. It showed that the messy, real-world, easy tasks were actually the hardest for abstract logic systems.
Second, the behavior-based focus. Rodney Brooks showed that intelligent behavior can emerge from simple, direct sensing to action loops. Just remember his motto, the world is its own best model, and the key method was that subsumption architecture.
Third is physical grounding. Even our most abstract thoughts, like language and math, are understood by simulating physical experiences. Think perceptual symbol systems.
And finally, number 4, developmental synergy. The mind and body grow together. Cognitive abilities are inseparable from motor development. You need physical interaction to learn, something we see in both human babies and modern learning robots.
And when you accept that the mind is so deeply tied to our physical form, the source material suggests that old rigid line between artificial and natural intelligence, it really starts to blur.
It does. And that leaves a really interesting question for you, for the listener, based on this whole idea of the extended mind. If your mind is distributed across your brain, your body, and your tools, how does your constant reliance on technology, like your smartphone, which is without a doubt a cognitive extension, how does that change the actual boundary of where your mind truly begins and ends?
Yeah.
Think about that next time you can't remember a phone number without reaching for your pocket. Where's that memory really stored?